Hello, good afternoon. We are Miranda, Valeria, and Andrea, and we're going to explain our X-ray phantom for the course of analysis of imaging systems. At CI3M, there are hundreds of thousands of X rays and CT scans yearly, critical for accurate diagnosis and patient care, but reliant on consistent image quality. Most existing QA phantoms are expensive, hard to transport, and also lack of standardized protocol for modern systems. Our project introduces a low-cost modular phantom and a reproducible acquisition protocol to simplify and enhance the quality at the learning partner station. We use the Philips VV Pulsera C-arm, a device used for aneurysm surgeries and pain management. It has features like pulse mode for better contrast, a rotating anode for long procedures, a rear wheel for easy transporting, and advanced settings for top performance. Together, these tools improve our quality process and meet operating room needs.
Our objectives are twofold. First, to develop a reproducible protocol that measures spatial resolution, contrast, noise, and uniformity. Second, to validate our results against international IEC AAPM benchmarks on our learning partner digital radiography and multi slice CT units. Note that we focus exclusively on phantom based measurements dose assessments in patients or therapeutic imaging lie outside this scope.
The heart of resolution is a three-module phantom held in a 3D printed multi-level holder. The base matrix is gelatin poured around the inserts. Module 1 tests spatial resolution with 7 slit separations from 3 cm down to zero point 0.1 cm. Module 2 evaluates contrast using Mexican 10 pesos coins and 5 pesos coins alongside staples, paper clips, aluminum foil, and cardboard. Finally, Module 3 simulates scatter with fine metal dust sprinkled through the area.
We acquire images using two different imaging modalities: digital radiography and computed tomography. For the digital radiography scans, we use a tube voltage of 70 kilovolts peak, a current time product of 5 milliampere seconds, and a source to image distance of 100 centimeters. We ensured that all phantom models were captured in a single projection. For CT, we selected a higher energy setting of 120 kilovolts peak and 250 milliamperes with a slice thickness of 1 millimeter and a pitch factor of 1. To maintain consistent positioning and alignment across scans, we mount the Phantom on a custom designed 3D printed jig. This helps us to guarantee a reproducible source to object distance and proper centering. Before each acquisition, we carried out mechanical and radiation safety checks in accordance with international standards, specifically EEC 612231 and the AMAPM Task Group 18 guidelines.
We then analyze the images using our MATLAB toolkit. Spatial resolution is quantified via the MTF cutoff from a slanted edge method. Contrast is measured as the C&R ratio of insert versus gelatin signal to noise. Noise is simply the standard deviation in a uniform region, and uniformity is the maximum percentage deviation across corner rows. We also assess repeatability by computing the coefficient of variation over repeated scans.
Here are example images. On the right, digital radiography projections on the same degree and showcasing the spatial model, and on the left, a single slice that captures all the three models simultaneously. We performed 5 replicate scans for each modality to test protocol robustness.
In the scans without metal dust, we were able to clearly resolve slit separations down to zero point 0.2 centimeters. When analyzing the modulation transfer function, or MTF, we found that the MTF 10 underscore cutoff was 5 line pairs per centimeter for digital radiography and 3 line pairs per centimeter for the CT scan. Both values exceed our minimum pass criterion of 1.5 line pairs per centimeter, indicating excellent spatial resolution in both modalities. Visually, the edges of the slits appear sharp and well defined with clear separation between lines. This further confirms the high image quality we achieved.
For contrast, the Mexican 10 and 5 coins produce two clear peaks in the grade level histogram. We measured a CNR of 4 for the 10 coin and 3 for the 5 coin, comfortably exceeding our target of 2. Line profiles through the coins versus gelatin further illustrate distinct signal separation. Background uniformity deviation remains under 2%, meeting our specification. With no dust, the Phantom shows minimal scatter haze. We measured a noise SD of just 3 Hounsfield on CT, or 4 grade levels on DR, giving an SNR of approximately 50. These values lie within our acceptable limit of under or equal 5 Hounsfield, confirming low baseline noise. Introducing metal dust adds a low frequency haze and slightly blurs the fine line pairs. Noise SD increases to 5 Hounsfield and CNR drops to 3 for the 10 coin and 2.5 for the 5 coin. The MTF also shifts from 5 to 4 line pairs per centimeter on DR and from 3 to 2.5 line pairs per centimeter on CT, quantifying the impact of scatter.
In conclusion, our low-cost Phantom and acquisition protocol meet and exceed the protocol's QA benchmarks for their radiographies. The 3D printed design is portable and reusable, and our MATLAB toolkit automates the metric extraction. Next, we plan to automate the scanning workflow, integrating the results into a QA dashboard, and this to extend this approach to the spec city or pet phantoms. We look forward to training these type of devices with the CI3M staff for adopting the protocol for routine. Thank you so much.